Hello everyone, welcome back to our NDT training session. I'm Muthulakshmi NDT Level I in 10 methods, API, PMP and Frozio Level 3 certification holder. And it's great to continue our journey into the world of non-destructive testing. In our previous session, we have discussed ferromagnetic material characteristics and the type of magnetizing currents. Now let's deliver into the another critical component of magnetic particle testing, that is magnetic particles and their properties. The quality and characteristics of these particles are paramount to achieving reliable and visible indication of discontinuities. Let's go to the session. First, what are the importance of magnetic particles? The type and quality of magnetic particles are critical for forming reliable and visible indications. If you make an incorrect particle choice, it can lead to missed indication, faint or undetectable indications, or even distorted patterns and misinterpretation. So, the type and quality of the magnetic particle is very important. The next is types of magnetic particles media. First, we categorize the media based on how the particles are applied. Dry method and wet method. First, we discuss about dry method. Here, the magnetic particles are applied as a dry powder without a liquid carrier. Think of it like dusting the part with fine powder. Next, wet method. In this method, the particles are suspended in liquid carrier. This carrier is typically water or a light petroleum distillate such as kerosene. Next, particle visibility types. For visibility, we have three main types of magnetic particles: visible, fluorescent and dual. Dual means visible plus fluorescent. Visible means color contrast. These are the particles you can easily see in white light. They rely on a strong color contrast with the test object surface to make the indication stand out. So next is fluorescent. These particles contain a fluorescent pigment and will glow brightly under UV light. They are excellent for inspection in darkened environments. Next is dual. Dual means visible plus fluorescent. As the name suggests, these particles offer the best of both worlds, working effectively in both white lights and under UV light. Let's move the next slide. Key particle properties. Now let's delve into what makes a good magnetic particle. First one is a magnetic permeability. High permeability is crucial. Already we discussed about what is permeability, because it helps the particles to be attract effectively to even low level leakage fields. These are the subtle magnetic fields that leak out from tiny discontinuities. However, high permeability alone does not ensure sensitivity. It must be carefully balanced with proper size, shape and quality of its suspension quality in the carrier liquid. For example, if you have highly permeable particles but they are too large and clumped together, they won't effectively form an indication. Next one is magnetic retentivity and cohesive force. These properties should be low for effective magnetic particles. Why? Because high retentivity leads to several problems. First one is magnetization during handling. Particles can become magnetized even before application, making them difficult to manage. Next one is background noise. They might stick indiscriminately to the surface, creating a haze that obscures actual indications. Next one is clumping on surfaces. They can form unwanted clumps. If they have high retentivity, they might stick to internal ferromagnetic components within the inspection equipment, leading to a loss of effective particles. Next is premature clustering. Particles might cluster too early before reaching the discontinuity, resulting in false or misleading indications. Next topic is suspension requirements. For the wet method, maintaining the quality of your particle suspension is vital. First one is concentration. You must maintain the correct concentration of magnetic particles in the carrier liquid. The liquid in industry standard is typically 0.1 to 0.4 ml of particles per 100 ml of carrier, which is often checked using a settling test. This is very important. If the concentration is too low, you won't get good indications. If the concentration is too high, you will get excessive background noise. Next one is vehicle replacement. It's essential to frequently replace the liquid carrier to remove contamination. Over time, the carrier can pick up dirt, grease, and other debris from the parts being inspected, which can interfere with particle mobility and indication formation. So, we move the next slide. Effects of particle size. The size and shape of magnetic particles significantly influence their ability to form clear and reliable indications, especially when dealing with weak magnetic leakage fields from small discontinuities. So, next one is dry powder particles. Smaller particles offer increased sensitivity to fine cracks. Imagine a very tight, hair thin crack. Smaller particles can better enter and define that flaw. However, they can behave like dust, meaning they may adhere indiscriminately to the surface, creating high background noise and potentially obscuring actual indications. Next, the larger particles are less sensitive to very fine cracks. They might be too big to enter the tight crack, but they are useful for detecting large discontinuities. They also help sweep finer particles, which can reduce background noise by cleaning areas where particles have stuck indiscriminately. The industry generally recommends using a balanced blend of small and large particles. Small particles provide sensitivity and mobility to get into those tight flaws, and large particles assist in building strong indications and help clean the surface, reducing the background. So we move the next slide. Wet method visible particles. These particles are generally much smaller than dry powder particles. The smaller size is crucial for detecting finer discontinuities in the wet method. Large particles in the wet suspension can be problematic. They settle quickly out of the suspension. They may become stranded, leading to false indication, for example, along drainage lines as a liquid flows of the part. Next one is wet method fluorescent particles. These are fluorescent coated magnetic particles, not just a mixture of loose fluorescent pigment and magnetic powder. If you have a loose mix, it leads to excessive background noise and dim or non-visible indications because the pigment is not properly attached to the magnetic particle. What are the manufacturing requirements? The fluorescent pigment must be chemically bonded or encapsulated around each magnetic particle. This bonding must be robust enough to resist solvents in petroleum based carriers. Surfactants means which help particles disperse, and mechanical wear from things like pumping and agitation in the suspension tank. The next slide is effect of particle shape. The shape of magnetic particles significantly influences how they interact with magnetic flux lines, form indications, and behave during application. Common shapes include spheres, rods, and flakes. Next topic is elongated particles. These needles or rods. These shapes are particularly effective. They align more strongly along magnetic flux lines. They also develop internal north and south pole better than spherical particles, which is key for attraction. This pole attraction causes them to form a string of particles, which in turn yields stronger and more visible indications. Imagine tiny magnet linking together to form a clear line. They are ideal for weak or diffuse leakage fields and very effective for wide shallow surface defect and even subsurface defects. Next is dry powder shapes. While elongated particles offer better sensitivity, they present dispersion challenges in the dry method. They may clump in blowers due to mechanical interlocking. It can also be difficult to create a uniform particle cloud for application. Therefore, balanced mixtures are often used to aid in creating an even application. Wet method particle shapes. Particle shape is less affected by the carrier in the wet method compared to dry powder. This is due to higher density and viscosity of the liquid vehicle, which slows particle movement and promotes alignment even for less favorable shapes. Furthermore, automatic alignment into elongated aggregates naturally occurs under local leakage fields in the wet bath. In wet bath only. Mechanical agitation in suspension tanks ensures even dispersion of particles throughout the bath. The next slide is visibility and contrast. Even if a perfect indication forms, the test is failure if the inspector cannot see it. That's why visibility and contrast are absolutely critical when selecting magnetic particle materials. First one is color selection. Natural metallic particles often appear silver grey color. Common iron oxide colors are black or red. Manufacturers also offer particles with bonded pigments in colors like white, black, red, blue and yellow. The color selection depends heavily on the surface finish of the part being inspected. White or yellow particles provide good contrast on dark surfaces like mill scale, dark surfaces. Black, red or blue particles are better suited for bright, polished or blasted surfaces. The goal is always to maximize the visible difference between the indication and the background. So next one is fluorescent particles. As discussed, fluorescent particles offer superior visibility in ultraviolet lights. Even a few particles can fluorescent brightly, making very fine indications stand out. While they might be slightly less magnetically sensitive than some visible particles, they are significantly higher contrast under UV light. More than makes up for this. They are ideal for dark environments with controlled lightings, such as in a dedicated inspection booth. Next one is lighting requirements. For proper fluorescent MPT, you must have a darkness level of 20 lux or 2 feet candles in the inspection area. This ensures that the UV light is the predominant source of illumination for the particles. The UV intensity at the test surface must be at least above the sufficient UV intensity is critical to make the fluorescent particles glow brightly enough to be seen. Next topic is particle mobility. For an indication to form, magnetic particles must move and collect at leakage fields created by discontinuities. This mobility is essential for test sensitivity and differs between dry and wet methods. Let's discuss with dry powder mobility and wet method mobility. First one is dry powder mobility. Ideal applications involves creating a uniform airborne cloud of particles. In this cloud, particles exhibit three-dimensional mobility in the air before they settle onto the surface. On the surface, inspecting vertical or overhead surfaces helps stimulate this effect, allowing particles more time to move to discontinuities. However, on horizontal surfaces, movement is more limited. Once the particles land, mobility can be enhanced in this case by tapping or vibrating the object using AC or half-wave DC, which improve particle response and mobility over full direct current. This relates back to our earlier discussion about the pulsating nature of AC and half-wave DC, which causes the particles to dance more, allowing them to overcome minor surface resistance and migrate to the leakage field. So next one is wet method mobility. In the wet method, particles are suspended in a liquid vehicle. They exhibit 2D mobility when flowing over the surfaces and 3D mobility when the object is immersed in the bath. What are the challenges includes? Particles settling out the suspension before reaching the discontinuity, ensuring the particles move effectively with the carrier and reach all surfaces of the part. The settling rate depends on few factors. Increased particle size and density difference between the particle and the carrier lead to an increased settling rate. Larger, heavier particles will drop faster. Next is increased viscosity of the carrier leads to decreased settling area or settling rate. A thicker fluid will keep particles suspended longer. This is the factors of settling rate. Next is media selection. Choosing the right media is crucial based on the specific inspection requirements. Dry method versus wet method selection. Type of discontinuity. The dry method is generally better for subsurface discontinuities. This is often paired with DC magnetization for deeper penetration. Next, the wet method is best for fine surface or broad, shallow cracks. This is typically used with AC for surface flaws or DC for slightly subsurface flaws. Next one is surface coverage. The wet method provides more complete and uniform coverage, especially beneficial for irregularly shaped parts, as the liquid can flow into all nooks and crannies. Next is convenience. Dry powder combined with portable half-wave units is ideal for on-site or field testing due to its portability and easy to set up. Wet method aerosol cans are convenient for spot checks in the field. Let's move on the next slide. Current type considerations. As we have discussed before, the current type profoundly impacts penetration due to the skin effect. AC combined with dry powder is good for surface cracks, but it is not suitable for subsurface discontinuities. The skin effect concentrates the magnetic field at the surface, and the direct current combined with the wet method helps in detecting some subsurface flaws as well due to its deeper magnetic field penetration. Next is visible versus fluorescent particles. Visible particles uses under normal lighting condition. They are more convenient as they don't require specialized lighting. However, they are less visible for very fine indications. Next one is fluorescent particles. Fluorescent particles must require UV light and a dark environment for viewing. They offer superior visibility and contrast, making them particularly effective for very fine defects that might be missed with visible particles. Next slide is magnetic particle testing processes, residual versus continuous method. Finally, let's look at the two primary application methods for MPT. First one is residual method, second one is continuous method. Residual method, in this method the object is first magnetized, then the magnetizing current is stopped, and only then they are magnetic particles applied. What are the key points? This method only works if the material has sufficient magnetic remanence or retentivity. This means the material must be able to retain enough residual magnetism to create a leakage field after the current is turned off. It is the best suited for detecting surface discontinuities, and it is commonly used with hot steels, which typically have low permeability but high remanence. Particle applications can be either dry or wet, that means immersion or spray. A dual time in the bath can improve particle buildup. Care is needed when removing the object from the bath or inspecting it to avoid disturbing weak indications. This is the residual method. The next is continuous method. In the continuous method, the magnetic particles are applied while magnetizing current is still on. This method is generally more sensitive than the residual method because the full magnetic field is present during particle application, providing a stronger pull for the particles. It is suitable for low carbon steels, which typically have low retentivity and therefore wouldn't work well with the residual method. And it is most commonly used with AC alternating current for excellent particle mobility, which, as we discussed, causes the particle to move more freely. Then careful timing of the current and bath application is crucial. If particles are applied after the current is turned off, there will be a significant loss of sensitivity. If the bath is applied after the current is turned off, indications may wash away before they can fully form or be observed. So next, high sensitivity sequence. Wet continuous method. This is wet continuous method. For achieving maximum sensitivity with the wet continuous method, particularly in an immersion setup, follow these sequences. Immerse the object in bath. Next one is apply the magnetizing current during immersion. This is very important. Next, keep current on during removal from the bath. Next, keep the current on during drainage. Stop the magnetizing current only after the part has drained. This specific sequence ensures maximum particle attraction at discontinuities because the magnetic field is active throughout the critical stages of particular application and formation. This covers the critical aspects for magnetic particles and their properties from our source. I will prepare some questions for this session. Comment your answers in the comment box. I hope this concept is now clear to everyone. If you have any further clarification, please drop them in the comment box. Thank you.